Okay, I'll do that. Let's actually get started. So I'm Carl. I'm PyPy core dev, and I'm talking today with Max, who is what was the formulation? What was I supposed to say?
I work on compilers for a social media company.
Right. Excellent. And so I've been working on this blog post or general like writing small compiler optimizers in the last couple of weeks, and Max has sort of helped me write them and given me feedback, and we bounced some stuff back and forth. And so we thought it might be, and we wrote one compiler pass beyond what I wrote in the blog post together. So we thought it might be fun to do some more work, and we thought it might be fun to do that publicly. So that's why we're streaming this thing here. And let's get started, Max. So what we did to prepare this was basically take the code from the blog post, but not really all of it, just basically the support code that we need to sort of define operations and define the intermediate representation of our imaginary compiler. And if you've read the blog post, then all this is familiar to you, but if you haven't, then we should probably talk about some of that, Max. Should we go through it a bit with a little bit of detail?
Sure. Also, what's an imaginary compiler? I mean, this is as real as any other compiler.
It doesn't really it's missing two of the ends of the sausage, right?
So no, it goes IR to IR. It's a compiler.
Right. It's an IR to IR compiler, and it's an optimizer. It doesn't have a front end. It doesn't have doesn't make any machine code. It's like a third of a compiler, basically. Right. So we didn't add any tests here, right? So that's a bit annoying. Should we start by writing a very first test that just shows the kind of problems that we want to run, optimize?
Sounds like a test. You have one test. It's the interpreter.
Oh yeah, that's true.
You want to write a string test?
Yeah. No. We can look at we can write one test basically. Yeah.
I don't know how to use PyTest. You don't give it anything? No. Okay.
No, you don't give it anything.
So, and then this new API, I got to take a look. All right, we'll just copy this. Alex store, load, escape, great, incredible.
Mm-hmm.
And then you can go. This will make it easier for everyone to follow along. And then I can do, what is it? BB to stir. Okay.
Yeah, BB to stir.
And we'll see it fail.
We should talk about the code a little bit, but
sure.
You can also run it to have it.
So let's make the basic block. Block has some arguments that come into it. And every instruction returns. Huh?
Yeah. Let me try to say something. So the idea of this code is that we have a little API that allows us to construct a basic block, and a basic block is basically a linear sequence of instructions. And so basically we instantiate a basic block, which is just line 165, and then we can add instructions to that basic block by calling methods the methods have the names of the instructions. So basically by saying bb.getArg0, it means we will add a getArg instruction to the basic block. And the argument of that getArg instruction is the constant 0. And we don't really need to look at how this is actually implemented, but the idea is that if we call these methods, we incrementally add instructions to the basic block. So first we add a getArg instruction, which returns a variable 0 as an argument. We store that there. And then we call an allog instruction, which will allocate a new object. And then we will add a store instruction, which stores something into the object at field 0. And the thing we will store into that newly allocated object is the argument that we're getting into the basic block. And then we'll reread the same field from the same object again, and then we'll escape it. Let's actually kill the escape, because we're not really going to use that in today's stream, I think. So right, and then we have a helper function that actually takes the basic block and turns it into a nicely readable string representation, and that's what Max is testing here. And the test will fail because bb to string actually returns a nice string, and it doesn't just return an empty string.
So I gotta do this VN thing again, because I forgot to set that up. So pardon me while I do that. Some nice Python sandboxing practices.
Yeah. Okay. I'll look at the comments. Hi, Hamura. Thanks for the feedback. And just in general, please just write questions, and I'm happy to, like, we're not particularly, we didn't really plan this through, so we'll just interrupt, and happy to answer questions at any point. Right.
Didn't like that. Oh, perfect. We want it to fail.
Right, we want it to fail, and the thing that it fails is actually the string representation that we get. So if you run it with verbose, you should get the string, I think. I don't know.
No, it didn't like that. All right, I'll just type it in manually. That's okay.
Yeah, sure.
What's a bit of typing between friends?
With your very loud keyboard.
Sorry, is it too loud?
No, it's fine. I'm just teasing you.
It's actually the quieter one.
Very authentic hackery.
Well, if I were really authentic, I'd have a happy hacking keyboard, but I don't.
Yeah, there's another test. One test we actually passed into file, but we won't necessarily look at that now. Thank you, Matti.
Yeah, so the first test is testing this abstract interpreter situation, or this interpreter, and then we have the string representation.
Oh, Niels, is that a passive-aggressive way of saying that the keyboard is too loud? Niels says, the audience appreciates a little less hackiness in this case, but there's nothing you can really do, right? So I think we will just, I fear you're going to have to live with it. Niels.
Yeah, for my next stream, for my next trick, I can find a different keyboard, but for now, this is the desktop computer, and this is the only keyboard I have on hand that'll work.
Oh yeah, right. Okay. Niels says, please don't get the louder one.
Okay,
that's fair.
Good.
That's fair. So cool. This should now pass, right?
Yeah.
So try it. You did. Right. Excellent. Very cool. Should we commit this?
Okay. I added some other changes, and I forgot to commit them, so we're going to do those first. It's just some minor typing things. Blah, blah, blah. Nobody cares about that. Okay. Okay. And otherwise, we have a test. Amazing.
Oh, hi, Anthony. Good to see you.
Is this Anthony Shaw?
No, Soti, I think. Hi, Thorsten. Right. So let's go to the test. Let's actually think what we want to do. So what Max and I did, and this will be a blog post very soon, we wrote an optimizer that is able to remove allocations that aren't needed. And actually, the current test that we wrote is an example. Can you open the editor again?
So which one?
Right. So yeah. And this in this like basic block, there's an allocation and then a store and a load, and then the object is just no longer used. So this could be optimized away. But that's not what we want to do. What we want to do tonight, right? What we want to do tonight is we want to think about optimizing stores and loads in the case where we didn't see the allocations, right? It's basically we want to see optimize stores and loads away in the situation where the objects are actually allocated before the current basic block. So let's actually
make sure that this extra load goes away.
Right. So basically, let's write a new test for that. I mean, we were just testing the string, and let's actually write the first test that we want to optimize, right? So that's load after store. We could call it load after store. Yeah. And then just remove the alloc.
Oh, remove the alloc?
Yeah. I mean,
we want
to make sure that we can optimize stuff that exists before the block, right? So we do a store into var0, and then we do a load from var0. Yeah, and store a 5 in there maybe.
Store what?
A 5, like some.
5, sure.
And then we need to do something with var1. var1, we could escape it. So I need to say something about escape. Escape is basically just a shortcut for any kind of side effect. You can think about it like it's some kind of print. And we just want to see that the argument to the escape is what we want it to be. Right. So that's the unoptimized string representation.
And this is we're escaping. In this case,
we're escaping.
It's going to be 5.
Yeah, sure, but you need to call the optimizer, right? Currently you're just converting BB to
let's call it optimize load store. Right.
Right. So wait, the load needs to go away though, right? I mean, that's the thing we want to optimize. Right. So what this test does is the basic block gets some kind of object, and it does a store into that object at offset 0. And then immediately afterwards, it does a load from the same offset 0 from the same object. And then we basically print the result using this slightly strange escape operation. And what we want to do, we want to write an optimizer that says, okay, I just stored the value there, and I'm loading it again. And that we know that it still has to be, the field still has to have the same content, right? Because we're assuming that there is basically no multi-threading going on here. I mean, even in a multi-threaded world, this optimization would mostly be possible in all memory models. But to make our lives much easier, we should just think about this as running in a completely single-threaded world.
Yeah, who needs threads?
Who needs threads? They're completely right. So let's start writing this optimization. Right. So the optimizer gets a basic block, and I would have just returned BB actually.
Oh yeah. Okay.
At least that's a valid. That's a valid optimizer.
You don't like deleting?
Not a very good one. Oh, by the way, given that we're not using video, we should switch to this view, I assume. Right. So we can run it and watch it fail.
Oh no! Why did it fail?
Oh no! Yeah, woe is us.
Like this.
Yeah, it fails because the load is still there, and the escape doesn't get the argument 5; it gets the argument var2. Right. Okay, so now we need to actually do work, right? So let's start with our basic structure of that all the optimizations in this toy world have. So all optimizations have the same structure. We create a new basic block, which is just empty at the beginning, and then we have a loop over all the optimization in our input basic block. So it's for op in B or something.
Is it, sorry?
It's for op in, like this, in BB.
Oh, you made an iterator? Okay.
And now, well, we can just say op BB append BB op. Right. And now we haven't run anything, right? We just made a copy, but but that's the basic structure. And let's actually not run the test because it will just fail in the same way. But let's write some actual code. So and now we need a number of cases for all the optimizations that we want to, for all the operations that we want to like optimize. Right. So the operations that we want to do something about is loaded store. So we need something like if op.name equals store.
Something like that.
Yeah, well, I mean, yes. We just need to put the right code into the process, right?
Oh, that's the easy part, you know.
And actually, I haven't planned this very far in advance. So yeah, I mean,
we'll have bugs.
We need to think. Okay. Sorry.
We'll have bugs.
Yeah, we'll have bugs. Yeah. Okay. We can use an elif in 181. That's true. Thank you, Matti. So
I mean, eventually it's good to have them say continue, I think. So it will just be an if, you know.
Yeah, that's true. But yeah, not always. Max, I know that's like being very annoying. Can you switch the cases, please? It fits my brain better. Right. So let's actually think about the example, right? So what we do in the example is we store something into position 0 of a certain variable, right? And we need to remember that somehow. So we need some kind of data structure that remembers the fact that we stored something into var 0. And that data structure is basically the knowledge that we get about the heap while we walk along this basic block, right? So the optimizer will take one instruction after the other, and then for every operations, it potentially learns something about the heap. And for a store, what it learns is that if you later read something from the pair variable comma position, then you can remove that and replace it with the second argument, right? With the third argument of the store operation. Does it make sense, Max?
It kind of sounds like you want to have your interpreter run at compile time.
Kind of, but I'm not sure it really helps. I mean, this point of view isn't super helpful. Yeah, we have some kind of metadata. And I think what I want to call that, I just want to make a dictionary before the loop. We can call that like heap knowledge or something.
Heap.
Yeah, maybe like compile time heap or whatever you want to call it. It's not the real heap, right? It's just the knowledge that the compiler gains about the heap. And yeah, we're assuming here that this is some kind of object-oriented, memory-safe, everything's beautiful, garbage-collected language. Right? So let's think about the type of the heap. And I think it's actually a dictionary that takes tools of values and positions as keys. And the values are values. So yeah, the int is the offset, Matti. Yeah. Does that make sense, Max? I think
so.
I mean, I'm sure we will have to refactor this, but I think that's a start.
I think we can also. I actually don't know the syntax for this. I think you have to do that. But
I have no idea. I'm not using the Python types very often, so.
That's because PyPy is in Python too.
Yeah. So that means you probably need to import tuple, though.
I think I did earlier.
Oh, you did. Well done. Okay, so that was finding the types was the hard part. Now we just write the code, right? So when we see a store, when we see a store, we learn something about the heap, and we should store that knowledge into our dictionary. So we should say compile-time heap op.getArg0, comma. Now we need to get the integer somehow. That's op.getArg1.value. We know that it has to be a constant always. We don't allow stores with a variable offset. I think there's a helper function for that. I'm not sure I pasted it for you, but maybe.
Well, we have. I don't know that I have that. I can set that it's. I can assume that it's a constant.
It would be after the classes, I think.
Oh. Well.
Yeah, get num. There's get num.
Where do you see
get underscore num?
Got it. Very nice.
Mm-hmm. And it takes the op and the index of the argument that you want to turn into a constant. Yeah, you don't. The default argument is for the offset is 1. For the index is 1, so you can leave that off.
Yeah, I'm just going to keep it for now.
Okay, fine. So, and that should be op.arg1. Right. Arg2. Yeah, sorry.
I mean,
so when we see a store, sorry, go ahead.
This looks like an interpreter.
It looks like an interpreter a little bit. Yeah. Now we can kill the paths, right? So now we learn some, like we saw the store, and learned some knowledge about this, like the heap, when passing the store. But we still have to emit the store, right? Because the optimized basic block will still have to actually do the modification of the objects at runtime.
So something else can remove the stores if the object.
Yeah, later. Some stores could be removed, but that's the next test. No, that's a few tests in the future. Torsten is asking, is this abstract interpretation? So, I mean, yes, but it's you would have to work relatively hard to sort of really show in which precise way this is abstract interpretation. So it's a bit of a cowboy coding version of abstract interpretation, and if you put enough effort into it, you can make this a precise form of abstract interpretation. But I mean, I'm not tonight, basically.
That sounds very academic.
Sorry, I am an academic, so I'm allowed to sound academic.
And I'm a cowboy. Yeehaw.
I'm a weird academic. I write code, right? So now we have this nice piece of knowledge in our compile-time heap, and we need to use it in the Aleph, right? So in the Aleph, we basically need 2 cases. We need to check whether we know something about the load that we're trying to emit, and if we know something about it, we can potentially remove the load. But then often we don't know anything about the load, and then we also can't remove it. Right.
Oh, this can't be a get. Oh yeah, it is.
Yeah, exactly. You're reading my mind, Max.
So the 2 cases.
Yes. So if we have exactly this key already in our compile-time heap, then we're good, right? Then we can remove the load, and we know that the result of the load is the value of this key in the compile-time heap, right? So you will need a op.make equal to. With this, we're telling the optimizer, we already know the result of this operation, and the result is, whatever we stored into the compile-time heap earlier, right? And then you can say continue, because you do not need to emit this operation, right?
So otherwise.
Yeah, otherwise we can just go to the generic case, just append something to the output. And I think that's probably enough to pass the first test.
So you're saying that some data structure holds equivalent values, and we've substituted the complex one, which is a load, with the value that was stored previously.
Mm-hmm. So
awesome.
When we see a store operation, we remember that we stored something into a certain variable at a field offset. And we do that in line 183. And then when we see a load of the same index out of the same variable, we can replace it with what we remembered putting there. Right?
So this assumes there's no like delete.
Oh yeah, sure. There's like a ton of assumptions. Can we check that it actually works? And then we need to fix 17 problems. Awesome.
Let's fix some of those problems one at a time.
Yeah, sure. Not all at once. Which problem were you trying to tell me about?
I don't think there's a problem. I'm making some assumptions clearer because.
Yeah, please make which assumption were you thinking about?
I don't know. I don't know what the instruction set is here. Oh, that's fine.
There's really no, just loaded. Yeah.
Delete.
So I think one of the problems is, one of the things we should test is, and I'm even fine with adding that to the current test, if you have a load from an unrelated field, like let's say there's another load that says load offset 2 from the same object.
Sure.
Then we cannot remove that. Yeah, so Thorsten is asking what happens if we store something to a dynamic address. And for now, I suggest that we think of these things really as like structs. And the offsets are really sort of always compile time static. But if we wanted to support something like an array, and then indeed it becomes a lot more complicated thinking about, oh, we store something at a dynamic address, and we don't really know what the value of the offset into the array is, and then we need to work again. And indeed, like a complete optimizer for these kinds of loads and stores would have to do that. But I think for tonight, I would like to focus on the cases where the offsets are always static and it's really more like a struct.
You mean something like this?
Yes, this is much harder. Right?
Yeah.
I mean, it's definitely harder. Yes. Okay, so this should also just work, I would hope. Can you try it?
Very nice.
Cool. So, okay. Now comes the actually hard test.
Should you ready to commit?
Oh yeah, sure. Please commit this.
Let's see. All right.
I really quite like your font. What is that, by the way?
This is Comic Sans.
Oh yeah, right.
The Comic Sans with
Comic Sans
code.
Mm-hmm. Awesome.
Someone on Twitter, their name escapes me presently, introduced me to this font, and it's phenomenal.
Yeah, no, I like it too. Yeah, Thorsten, yeah, absolutely. You basically you can make all these things work, and I mean, like a quote unquote production optimizer for this kind of stuff will make them work. Like the PyPy JIT has optimizations for exactly these cases, but yeah, that's sort of running before we can walk. I mean, right now the optimizer is buggy, and
that might work.
We should fix that first.
At present, this one, right? His current case, this does some amount of constant propagation already, right?
Well, we're not running that yet, but it could be. We could combine it with the code from the blog post, and then it would work absolutely.
Oh, it's all missing. Got it. Okay, noted.
Yeah, it's not. I didn't give you that code. So let's think about a bug. What happens if we we need two objects, right? And we store into offset 0 of both of them. Can we cache the load for both of them or not?
So you mean that let's make a new test. You store
you have two vars, var1 and var0 and var1, right? And then you store into position 0 of both of them, 5 and 7, say. Right?
7, okay.
Is it now valid to remove, and now you load both of these fields again?
Sure.
That needs to be var2 and, yeah. And var1, exactly, and then you escape them both. Is it valid to remove both of the loads?
Well, why not?
Well, why not? I mean,
it seems like
this stuff is
we
full
can
of
do what we did last time, and
last time we could, but today we can't. So this is full of traps, and this is the most important trap. The trap is that var0 and var1 are arguments to our basic block, so they could point to the same object, right? So var0 and var1 could alias, and then it's not valid to remove the second load, right? No, to remove the first load. The second load is fine, but the first load isn't fine. To remove the first load isn't fine. Does that make sense?
Yeah, I don't like this. Yeah. This isn't fun. Why would you do that?
Well, I mean, it's allowed, right? If you have a function f that takes a and b, nobody prevents you from passing the same object twice in there, right?
All right. Let's write some.
Let's write what we expect, and then we see what we get. We definitely need both of the stores. 7. Yep.
And then you load from which one are you saying should exist?
So the second store wins, right? So we cannot remove the first load because the first load gets from the the other way around. You need to leave var0, 0, and the second load can be removed.
Got it.
But the index is 0 in the load.
The index is you're right.
Yes. No, and here this is var2, and the second thing is 7. This is what we need to produce, and we're currently not producing. Try it. Let's see what that fails. Right. Currently, it looks like we removed them both. Can you run it with VV? Is that really better?
Actually, it seems worse.
No, this is now a nice unified diff. We're expecting a load and escape, and we're getting 2 escapes.
You're expecting, and we're getting.
We're expecting a load and 2 escapes, and we're getting just the 2 escapes.
Got it.
Yeah. So now we need to think, right? And this is really the hard part.
So how do we say they might alias?
So what we need to do is we need to throw away some of the information in our compile time heap, right? And we need to throw away that all the information that could be affected by the store, right? So let's think about which optimization, like which information can be affected by the store to offset 0.
So assuming that everything is like storing 1 byte and we don't have to worry about overlap and stuff.
We won't. Let's assume there's never any overlap.
Okay. We want to go through and remove everything at that offset? Is that what you're saying?
Yes, exactly. So we need to remove every entry in compile time heap that has the same offset as the current store operation that we're seeing. And then the only operation that we can leave is the one that we currently have, right? So the last write wins.
Okay.
That's an easy write.
So we want 4.
Maybe we just make a copy of the compile time heap, because otherwise we would have to mutate the dict while iterating over it. That's a bit iffy.
Oh, I was just going to mutate it while iterating over it, but I guess that makes sense. We shouldn't do that. Sure. So.
And yeah, I would actually do it the other way around. I would start with an empty heap, and we put everything into the copy that we know is safe to put there.
Makes sense. So Mati says you want to remove the key when you see a load, not a store, right?
I think it's the other way around. I mean, you need to remove a store, could potentially mutate every other variable in your program, right? Because you don't know whether any of the other variables store like an alias to the same object that you're currently mutating. So a store can really have, I mean, a load cannot have side effects. A load doesn't have side effects, right? But the store does. So the store can invalidate some of the knowledge in the compile time heap that we're storing information that we know about.
In the test, this is not the most recent test. There's 2 stores and 2 loads.
Right. This is the
This is the one we're trying to get to work right now.
Yeah. So there are 2 stores and 2 loads, and the stores both need to stay, but only the second load can be removed. No worries. I mean, just in general, if this stuff is tricky, it feels tricky. It definitely is tricky. I mean, if you get it wrong, you're also very annoyed because it leads to miscomputation. So I mean, it's definitely a good idea to think about it carefully.
So we want to say the current key, and then compare the 2. So
no, we need to just compare the offset, right?
Okay.
The variable. I mean, it's important that the variable doesn't matter, right? Because the variable. I mean, we don't know how much the variable's alias.
So if key 1, which is the offset, is the offset, or is not the offset, we put it in.
Yeah, exactly.
Okay. Heap copy of
key equal value. Yep.
Okay.
And that's
so let's
fine.
leave a comment
so
because
now,
future me is going to be confused in like 5 minutes.
Yeah, put a comment there, please.
Objects and alias. So we have to remove potentially conflicting rights. Is that a reasonable thing to?
Yes, I do think so.
All right.
Everything's getting more complicated, so it necessarily needs to get smaller. Yeah, and I think the rest is fine, because after we threw out all the things that we potentially, like, we threw out some knowledge that we had to invalidate potentially, right? And so now we put back the stuff that we know for sure is still has to remain true. Right? Does that make sense?
I think that makes sense.
Great. So who else does it make sense to in the chat, or I mean, for whom does it not make sense? Let's run the test. I think that's a good thing to do.
Oh no. Was this intentional on your part, or did I just mess it up?
No. This is not planned.
Did I escape?
No, but that's just a variable numbering problem, I think.
Let's see. We want to escape.
We want to escape bar 4, not bar 2. Hi, Face. Thank you for the reassurance.
And then the look.
Cool. So we just had a typo. I think it passes now.
Very nice.
Awesome. High five.
High five. Oops. Right. Let's make a commit.
Yes, please.
So we've done this complicated thing. We've added a test. Phenomenal. Support. Oh, that's a great point. There are tests with the same name.
So let's call this two stores. Right. And actually, you know what we should do? I mean, please commit this first. But then there's another test we should write.
It really looks terrible in this typeface, but that's a face with open mouth.
That's amazing. And we should write a test that makes sure that we are writing to different offsets. We can still remove both loads.
Yes, right? Great idea. So I can copy this one. And then...
No, you can copy the second one, and the second one is better to copy.
Right. And then this load should be gone, and this should be 5.
You're too quick for me. Line 2, 4, 3. Wait. 2, 4, 3, exactly. And now it should work.
Oh no,
it doesn't. Oh no, it's just a variable numbering problem. Go back. It will be at the bottom. 252 should be 4 and 5. Yeah, face. That's absolutely correct. But for freshly allocated objects, you want to do much better. And it's a bit mean to not get to that tonight, because that's what Max and I did a couple of days ago when we just zoomed without streaming, and there will be a nice write-up of that coming soon, I hope. But yeah, I mean, actually, I would argue that the case where we do allocate, where we do see the allocations, is kind of more important than what we're doing now. But yeah, tonight we decided to focus on the case where we don't, where the code that we're analyzing doesn't contain the allocations of the objects. Right. What else do we need to test? But yeah, I mean, thinking about allocations is a fantastic suggestion, and it's where the real wins actually come from. Max, what else do we need to test?
That's a great question.
I think we could think about the next feature. I'm actually not too unhappy with what we have so far. And the next feature is, right now we can remove a load after we've seen a store. But sometimes you see loads from the same offset, from the same variable, directly after each other. And we want to remove the second one too.
We should test loads in between stores.
You mean the one where they share the offset, I assume, because
yes,
otherwise it just, right, we can do that.
Which, is not really materially different, but
I mean, it's good to be paranoid here. So I'm all for being paranoid.
All right, so we store 5 at 0, we load it. We store 7 at 0, we load it, and then we escape them both. Right? Does that make sense?
Cody Face, yeah, sorry, I was reading the chat. Yeah, that makes sense. I'll answer the question. Let's finish the test and I'll answer the question. The stores stay.
This
the loads
go away.
We can't do that yet.
We can't.
That's actually super advanced. Let's not think about removing stores yet.
Okay.
If we can remove the 2 loads, that's already pretty good.
Great. So this should be escape 5, 7.
Right. So to answer QWERTY Face, yeah, absolutely. So if you see the allocation, we want to avoid the allocation entirely. It's even stronger than just until they escape. We can avoid the allocation. We can sync the allocation to the point where they escape and remove the loads and stores from the allocated object that happen between where the object is created and where it escapes. And yeah, I mean, the write-up of that will come very soon. And Chicken Brooder, hi, amazing Nick. We don't have a test for load and then store yet, right?
Well, we do now. I just wrote it.
You did. Does it pass?
I don't know. It's a good question. Yes.
Yeah. Cool. Let's go with that. I have a nice next test to write, and then after that we will do what Chicken Brooder was suggesting. So what I want to do now is 2 loads in a row. Like if we just load from the same thing twice, we know that the second load is redundant, right?
All right. So we just want to have 2 loads. That's it.
Yep. And we escape them both, and we should see that the first load stays, the second load gets removed, and the variable that we escape is the same. That's good.
Like that.
Yep. And that shouldn't pass. That's really a new feature that we don't have yet.
Oh no. I guess.
Yeah. Well, I mean, it doesn't pass. It cannot remove the second load. Right now, right now we can't optimize this.
It can't remove the second load because. Whoa. I'll make it bigger
Because
again
we don't.
in a second.
No. This is too small. I can't read that. I feel okay. You can't split.
I'll bring it back in a second, but
okay.
We can't remove it because we didn't put it in there because of we're only storing stores in the heap.
Yes, we don't learn anything from loads so far, right? I mean, we can also, like, our abstract model of the heap also gets information from loads, right? Because we know that after a load, like at runtime, the heap won't change, but our compile time heap says, oh, we already did that load, right? So when we see it again, we can just reuse the previous result. So we should mutate the compile time heap also in those loads that we cannot optimize away.
And that's okay because we're obliterating the same offset stuff every write.
Yes. But the cool thing is, for loads, we don't need to obliterate any other offset, right?
Right.
Because loads cannot mutate anything. So, so basically, after the continue, you write compile time heap square bracket load info equal op. And this means when we did the load already. Here's the keys for the load, and the result of that load is op. Right.
And so all of the other ones will be equal to that, because next time it sees it, it'll make it equal to. That's nice. That's pretty slick.
Yes, exactly. Yeah. Right.
Wow.
Nice. Cool. New feature.
Let's see. We add that, and that was one line. It's very cool.
Mm-hmm.
What would you call this?
This is a load after load optimization. So Matti says, is that always true, even if there are more stores? No, it's not true. If there's a store in between, the store invalidation logic will remove those entries. So it should already work.
So because we have this thing that says remove everything with the same offset.
Yes, exactly.
That's the only reason we can do this.
Yes, because the logic in store is already has the correct complication.
So we should see two failing tests if I remove this stuff.
Well, let's actually write the load store load test that Matti wants to check, and then we can add the test that Chicken Breeder suggested, because that should also now pass. Oh no, it doesn't pass, but it's a good next thing to work on.
So test load store load.
Yep. Matti, I'm getting to your suggestion in a second. We could even let's be a little bit more tricky here. Let's actually store to another object.
Oh, there's too many variables.
Yes. I mean, it's definitely completely easy to completely get lost in a sea of operations still.
Oh, we use different numbering schemes. Hold on. Okay, so we're storing in arg1. And then we're loading from arg2.
No, wait. We're loading from arg1, then we're storing in arg2, and then we're loading from arg1 again, and the second load is not safe.
Got it. So we can't actually that, they could alias.
Yes, exactly, because arg1 and arg2 could be the same object. Actually, a simple way to write this test is to say bb to str of op bb should be the same as bb to str of bb, because we cannot optimize this. Yeah. Mm-hmm.
Okay.
Right.
Wow.
Cool. And so Matti wants a new to fix the comment in 186. Yes. Actually, so the compile time heap is it doesn't really just store writes. I mean, a good way to think about it, and maybe we can write that into a comment. The compile time heap basically stores things we know about the heap, and this information can come from either stores or loads. Mm-hmm. Great. Cool. Good. So now let's actually do what we've been planning to do since a while, and that's a new feature. So yeah, good. Come with that.
Right.
Mm-hmm. Nice. So now we should add a new test. And
okay.
This will be a store after store optimization.
Store after store.
Yeah, I mean, it's basically what Chickenbruder has been suggesting, but we will express it in the traditional way first, and then their test should also just pass.
Well, Chickenbruder says store after a load.
Yeah. So what they say is, yeah, exactly. So and the example is you load something and then you store the same thing back, right? And that the store can be removed. But traditionally, this is called store after store, and yeah, we can write it either way. It doesn't matter much. So what we do is, the logic is, if we see a store and we know that the field that we're storing already has that value, we can just leave off the store. Right?
Okay, so we want to store that and then load it.
We don't have to load it, because removing a store is pretty significant in of itself, right? I mean, it's removing something that has a side effect.
So we want to make this, we want to say the store goes away, we just escape the load.
Exactly.
And then we say bar1 is load from bar 0 at 0, and then bar2 is escape bar1.
And that's it. Nice. And that
Thank you,
fail.
Reggie. That's very kind. As a former professor of mine, Norman Ramsey, puts it, we are typists first and programmers second. And I'm a terrible typist. All right. Does this work? Probably not, right?
No, it shouldn't. I mean, currently we are never removing any stores, right?
Yeah, we've got this extra store and this extra escape.
Yeah.
Great.
Okay, so what do? So we need to go to the store case.
On the store.
Yeah. We need to go to the store case and ask our heap model, do we happen to know that the store that we're trying to do, like the value that we're trying to store, is already at that offset in the object? And you need to do that before you're changing the compile time heap.
Before I even remove the other. Oh, you're right. Okay.
So
I'm going to do this again.
Maybe that's actually, no, that's too risky. Let's actually do it at the bottom, because then we know that we're safe and we can think about making it stronger afterwards. Right.
Okay. So in that case, we should have two tests. We should have one with an alias and one without.
Yeah, but yeah, let's start with the safe version. And the safe version is that we do all the invalidation logic that we used to have. We keep that, and
right. So we want to say if store info in compile time heap.
Yeah, and more. The condition continues, right?
Oh, okay.
You could say if compile, yeah, and the value of like compile time heap square bracket store info.
Oh, in that case, I should do a get.
Yeah, we should.
Okay.
Actually, do the get before, yes. Yeah, perfect. So if current value is not none, right? And now we need, there's an equal function. I'm not sure I copied it for you. Can you say like equal underscore tab? No, EQ underscore, sorry. Nope. So we might have to write that. So
what's equal to what?
Yeah, you need a function that's called EQ underscore value, and it takes two values. And
okay.
if if the two arguments, should I paste it? I'll paste it for you. Let me find it.
Okay. Well, it's instructive to type it.
Okay,
You can dictate
type it.
I'll put it by the other free function. It's called a getNum.
Yeah.
Some Python programmers might be wondering why this isn't the thundereq method on value.
It could be. In that case, you should call the arguments self and other. No, just kidding. Left and right is fine. So if they're both constants, we're comparing them by the value, and otherwise we just compare them by identity.
So return left.value is right.value.
Otherwise, return left is right.
Right. So if they're actually the same object,
like if they're the same object, and the same object on this level means the same operation, right?
What if one of them forwards to the other?
That's already dealt with because we're calling find to even get them. Right.
Smart.
That's hidden in the arg methods now.
I forgot about that. I made you write that function a couple days ago.
Yeah, that's right.
Okay, so we get the thing and then we forward it. So it should be the identical object.
Yes.
Great. So, I love pointer chasing.
Yeah. Right. Okay, so we're getting lost in the weeds a little bit. We need to use this function in our store implementation. EQ value, current value, and opt.arg2. Yes.
Okay, so
and if it's already the same, we can remove the store. That means we put a continue here.
Okay, so no sense storing again if the values are identical.
I mean, yeah, maybe you can say what the values are and write something like no sense storing again if the value of the field is identical to the value we're trying to store. Yeah, nice.
Okay, so we might know this from a previous store or load. Mati, yes, we know it'll pass the test, but also MyPy won't like it. So I could write optional, but
MyPy won't write it.
Yeah, I made this compile time type with MyPy.
Yes, it's all good. I also Mati's right, but I also kind of like. I mean, I would like to be even more explicit and write if current value is not none. Yes, thank you. Because for me, this really shows the intent a bit better, because we want to say if we have any information and the information is the same, then we do the thing, and otherwise we don't.
So we could be pretty clever. No, we can't be clever. Never mind. I take it back.
Let's try to see whether this works. Right.
Okay. No.
The store isn't gone.
Well,
to the debugger or something.
Oh no, we're gonna reason this through. I don't like debuggers. That's not true. I like debuggers, but I don't like going first at a debugger without any knowledge of what's going on. So we have a load and then a store of the same thing. And then we escape.
And we don't. Oh no! I know what's happening. Can you go back? Okay, I didn't need the debugger.
You were right. Tell me directly and instead give me a hint.
You can stare at the code. It'll come to you.
Oh yeah,
the hint is
people to just see me stare at it.
You're staring very beautifully. Unfortunately, we can't see you because your camera is off.
So,
So, so what's happening is we're very nicely cleaning. Oh yeah, I need to wait. In order for this to work, I need to switch the layout. There you go. Okay, back to the code. So what's happening is that we very nicely clean up the heap, right? So we're cleaning up. We're removing the value that we would need to decide,
yes.
right? So you need to do this get before the for loop, right?
Okay.
Mm-hmm.
Now,
Wait.
I don't know if that's correct.
I think that's correct.
Because
the store hasn't happened yet, right? So we are asking about information about the heap before we do the store.
The store hasn't happened, but we've also removed all of the rights to that field, haven't we?
We have, yes. And I'm also not completely sure that's correct, but it should make us pass our test. And it's, I mean, it might be incorrect on the good side, right? It might mean that we're not optimizing enough, but that's always better than optimizing incorrectly.
Sure.
I mean, so we might lose too much information. Okay. We might lose too much information, but that's always better than optimizing incorrectly.
All right, so it does pass.
Right. It does pass, and now we can think. I'm actually, yeah. So there's another test that we should write that doesn't pass, because I mean, we should. There are two tests we should write. This one I want to defer a little bit even.
Okay.
You should rename the previous one to load then store, because it's not a store after store. There's only one store. And now I want to write the test that does an actual store after store. Like just do the same store twice. Mm-hmm. Yeah, you don't need to get the names. No, don't do that. You don't need, the store doesn't have a result. Escaping that doesn't make sense. The only thing you need to do is you need to, I mean, what we want to see is that the second store gets removed.
Okay. So we just want store.
I think it doesn't.
Var 0, 0. And we want to do this.
Var 1 doesn't exist. Just put a 5 in there.
Oh, yeah.
So, and then in the test, you also need to say comma 5. Mm-hmm. No, wait, 0, comma 5. Mm-hmm. Nice. I'll try it. And I feel fails. No. Darn it. Okay. No, it's good. It's good. I know why it doesn't fail. But there's another test that will fail.
Okay.
Can you try? Let me think. Can you try to copy load then store? Right. And rename it to load then store then load.
I mean, at some point, people are going to wonder why this is kind of arbitrary sounding. This is why I like generally writing my tests with extremely clear names about what I expect. But we're not doing that here.
Feel free to make the names beautiful.
Yeah, it's some other time.
On your own time.
Yeah.
I'm not paying you for that.
You're not paying me at all.
Yeah, that's true. Only in fame.
I'm famous to 3 viewers. It's wonderful.
Yes. So we do the same load again, and we want to make sure that the second load still works. Right. The load should still be removed, and I think that might fail right now.
So you think just like this?
No, you need a second escape.
Oh. Huh.
Oh, there's a secret extra viewer that just looks at the same screen.
Woof. Let's see. Is this really var3 is escape the same?
It should escape the same thing, yeah.
Okay.
Maybe I'm being too pessimistic and it just works.
All right, so we have a load.
We're getting rid of the store, but we're not getting rid of the second load. You want to figure it out, or should I tell you?
Well,
look at the store case again.
Which?
Look at the code where we remove stores. Right. And the trick is line 206. So.
We want to do the old value. No, we don't. What?
We cleaned the old value, right? Because we very carefully went over our compile time heap and removed everything with the same offset. And then if we cannot remove the store, we nicely put it back in line 206. But if we do remove the store, then the continue prevents line 206 from executing. So what you need to do is move 206 before the if.
Yeah, that makes sense. That'd be a problem if we just didn't update the heap.
Sorry, I didn't get that remark. What were you trying to say?
No, this is great.
Okay, so let's commit that.
Okay, so we added a lot of stuff here. So what do we want to say? We want to say.
Oh, by the way, thanks for introducing me to git commit verbose. That's a fantastic
wonderful
feature. Yeah, because it means you can also you can tab complete all the names that appear in your diff into your commit message. So that's really good.
You might. You have HG though for PyPy. I don't know if so our fork of HG, which might give you more information about where I work, has -v, but I don't know if it's yours.
It doesn't, but there's a nice hack to still get it, so it works for me. Okay, so let's actually close parentheses. Let's actually do what we were trying to do.
Right, but what are we going to call this? We're going to say that we.
That's a remove. Classically, it's a store after store optimization, right? Curly face, I completely agree. This is the most interesting stream ever. So all the other people who aren't here are definitely missing out. I'm fine with this. I think that accurately describes what we're doing, and we just.
Right.
So but I agree that we want to think a little bit about aliasing, right?
That sounds good. Now that you've mentioned aliasing, which I hadn't considered at all, I'm very nervous about it.
About what?
Aliasing. I mean, I feel like I have to go audit every single line of code I've written ever in RJIT.
Yes, have fun. So let's think. So what we want to do is we want to have two objects, and we want to store, we want to load from both of them, then store the same value back into one of them, right? put it at the very bottom because it's going to be the most complicated test that we have so far.
Okay. So we have test, load, store, erasing. And then we've got two objects, you said. I liked when we did zero-based indexing because then it matched up with the index of the thing.
I think you're not consistent, and I'm fine with just switching to zero-based here.
You're right, I am not consistent. I'll change the other ones later. And then you said we want to store into one?
No, we load both of them.
Okay. From the same index. Oh no. Too greedy. Okay.
Right. And then we want to store into arg0, and we want to store back the same value.
Right.
And then we escape. Well, I don't know. Then we might load both of the fields again. And then we need to think. Then we need to think whether we can remove those loads. Right. So escape 3 and 4, basically.
Okay.
So now it's a difficult problem.
So that means we can the two loads have to stay, the first two.
The first two definitely have it, because we don't know anything about these objects, right?
The first store
can definitely be removed.
Can go away.
And the question is, does this and the third load can also go away, right? Because we did the store, even though we managed to remove the store, but it means we still know what's in that field of that object. The question is, can the last load stay? I mean, does the last load have to stay, or can it go? And I think we need to consider.
It has to.
I would argue that it doesn't have to, but I think we need to very carefully think through the two cases here to make sure that we're not getting it wrong.
Okay, so say they do. By the way, I'm curious, incidentally, if it makes sense to ever divide your code into, like, at runtime they're the same thing, or they're definitely not the same thing, because you might have two totally different.
Yeah, so that's a great question, and C compilers will do that. So C compilers, I'm not sure they can do it automatically, but you can basically add some weird attributes, and then they will really produce two versions and basically have a runtime check saying, are they the same? If yes, go that way, and then it's better. Are they different? If yes, go that other way, and then we know they're different, and that also gives us information. Right?
Do you do that in PyPy at all?
So in PyPy, we don't really do this. Let's just introduce a check, right? In PyPy, we have some aliasing, like sources of aliasing information, and when we know that two objects can never alias, we're able to invalidate the heap less on stores, right?
That makes sense.
And I mean, the most obvious source of aliasing information is if we know that the types are different, right? One of them is a subtype of the other. They might have the same kind of types of fields if we're just accessing the fields of the base type. But given if the types are different, we know that they must not, like they're definitely not able to alias.
Right. So you other things give you hints that you then can use to determine if they alias.
I mean, that's really the only aliasing information that we're using so far, and I want to like have other sources like since years basically, but it's fairly tricky to get right, and you need to be super careful that you're not producing like misoptimization. So I'm still thinking about it. like express it in just the right way.
Right.
And yeah, what I would like to do to understand this example is I would like to think about the two cases separately, right?
Okay. So say they don't alias, they're different objects.
So if they're different objects, then the store to arg0 doesn't affect to arg1, and that means we can remove both loads.
Okay, hold on. So if they're
should we write this into a comment?
Objects, I'm going to actually just go through and remove things. If they're different objects, then this goes away, this goes away,
Mm-hmm.
and this goes away because we've already loaded it.
Yes.
Okay.
I mean, the second load goes away because we know that the store is to a different object, so it means we can reuse the result of the second load. Yes. Okay, so in the not aliasing case, we will just keep the first two loads, right?
And right.
Can you please write that as a comment?
Yeah.
Because like afterwards.
Yeah. In the non-aliasing case, arg0 is not arg1. Then we can remove var2 because we are storing the result of a read. var3 because we know what we just stored, right?
Mm-hmm. Yes.
In var2, var4 because we know the store in var2 did not affect arg1, and we already have a load, right?
Mm-hmm.
Okay, so then in the aliasing case, arg0 is arg1. I guess I should use is here.
Yes.
Then we can remove. Okay, so that means that if they're the same thing, we remove the load. So we remove.
So if they're the same thing, we would if we would remove that load, we would definitely remove the store, and we would also remove the next two loads, obviously. Yes.
Okay.
Right.
Wow, shoot, you're right. We could remove it.
So, but that means we can remove the intersection of the things of the two cases, right? So in both cases, it's actually safe to remove the store and then both loads.
Okay, so we can remove var1 because we have already loaded off the same object in var0.
Mm-hmm.
We can remove var2 because we are storing what we just loaded, or just storing, what did I say? The results of a read. var3 because we know what we just stored in var2, and also var4 because
well, ditto. I mean, for the same reason as var3.
For the same reason as above. Because we don't know if they alias or not, we can only remove the intersection of the above two cases, var2, var3, var4. Okay. Oh, it should be below the escapes.
So that explains what we're expecting, and then I think it fails right now.
Let's find out. Let me load. Oh man. Okay. var2 is load. var0, 0. We want it to be We still want the
We
second
need the
load.
we definitely still need the second load.
And then we just have escapes.
And then we just have to escapes, but it's important that they escape the two different variables. Yes.
So 2 and 3,
Right.
the two different loads.
Yeah, and this works for both cases, right? I mean, if they alias, we load the same field from the same object twice, but it doesn't matter, right? And we
Right.
use two different variables, but so that's still fine. It's just that if they don't alias, we need the two different loads, obviously.
Right.
And so what I learned from this analysis is that basically when we remove a store, we don't need to clean up the heap, right? Because we really don't have to do the store. That means we don't need to do the invalidations that are normally necessary if we emit
So
a
you're
store.
saying we can put the continue above the loop.
Yes, I think that's what I'm saying.
Well,
But can we watch the test fail first?
Yeah. Wow, that's silly.
What happened? Oh yeah, great.
All right.
Wait. Right. There's a load too much. Yes, there are 3 loads currently, and we only want 2 loads.
Okay. So, and if you're saying if we put this continue, or we move current value and new value, then we do this.
Yes, and the heap copy in 190 can go down after the continue.
Right.
Yeah. And we should. Wow. Excellent. Should we? Do we need to fix comments, or are we happy with this?
This is kind of tricky to explain outside of a particular case. How would you explain that it's okay that we're ignoring the conflicts?
Well, I would say that the store isn't necessary, so the heap is actually unchanged, and that means we don't have to remove any heap knowledge that we gained so far.
Okay, so since we are not writing to the heap in this case, the heap is unchanged, so we don't need to. What was your phrasing?
Invalidate any of the heap knowledge that we gained so far.
Nice. All right.
Cool. So I think my brain is pretty fried, but I want to commit this, and then there's one final test that I want to write, and I don't want to. I mean, we're not going to manage the implementation, but let's at least write the test.
In the case where a store does not change anything, I guess. What was the other? You said what's the new test you want to add?
What I'm trying to say is that I probably there's one sort of hard case of things that we can't currently do, and I might be too exhausted tonight to still get to that. But I would love
We can write
to
the test and then leave it as an exercise for the watcher.
Yes, an exercise for the watcher. That's very mathematical, academic. We can also think about how we would do it for a minute, but probably we probably won't get to it. So, and if I remember correctly, there was like a hint in one of the questions to that already. What happens? Right. I think what Chicken Buddha wants actually would do that. So what I would like to do is right now what we can do is we can do a store, and the store of the same thing you can remove it. But actually it's fine to say we do a store, and then we store a different value into the same field. Right?
So we want to do var0 is store something.
5. And then store 7.
Okay.
And now do a load. Or, yeah. And then do an escape of var2. So what
this
was
should
the
remove
ideal?
the first store.
Yes.
But you think it doesn't right now?
No, because right now we can only remove stores if the thing we're storing is already the same value that's in the object.
Okay. So we want one is store our var007, and then var2 is
Escape of 7.
No, we don't even want that. We want escape var1. Ideally.
No, escape of 7.
Ah. Yes.
Yes. And I think if we could, yeah. Right. Should we think about it for a moment?
What do you want to think about?
So how would we do that?
Oh, how we would make it pass. We'll see if it does. All right, as expected. Well, it kind of seems like our allocation removal hacking the other day.
A little bit, yes. Goes in a similar direction. So what we would do is one way to implement this is by saying we delay a store. We cannot delay very many stores because it's very easy to get confused. But we can say whenever we see a store, we just sort of optimistically just don't emit it and remember one of these stores. Right? And then when
remember when it escapes, you emit all the stores that you would sort of put in the compile time heap for that object.
I think it's better to use a separate data structure than the compile time heap.
Okay.
Because the compile time heap contains things that you know for sure, but the other data structure is really things you still need to remember to do. And that one is, in some sense, much more crucial, because if you really, it means basically the compile time heap can get out of sync with the real heap a little bit. Right? If you just remove the store optimistically, you don't quite know. You need to remember to put it back if necessary. And so it's better to just put that into its own thing.
So you want to have a different structure that is like, you called it object info or virtual object in our last.
I think there's a really, really, really simple way to go about this, and that is to just have a single store, like just one operation that we have around, and it's usually none. But then when we delay a store, we just set it to the store that we delay. And when the next store is into the same object at the same offset, we can just throw out the delayed store, right? But it all gets pretty tricky, because the question is, when do we actually put the store back, right? Like,
if anything uses the result of the field, right?
So here's a question, Max. Here's a question for you. Would it be equally allowed to swap store and escape 7 in this example? We don't quite know what escape does, right? If it's basically a function that can inspect arbitrary objects, right, then it wouldn't be safe. But if it can only inspect the argument, then it would be.
Right. You have to have some notion of heap effects.
Yes. So I mean, this is really a kind of a tricky test, and we would have to think a little bit harder about sort of the semantics of our tiny IR. Right? So yeah, I mean, if you're good with that, I think we'll leave it at that, and basically there's a whole universe of things we can still do in that space. And indeed, if you push it far enough, then the test that Chicken Bula suggests would also pass, right? Like if you swap fields around, then swap them back. You just need to delay the stores for long enough that you notice that, oh, now things are back in the situation they was at the very beginning, and then we just don't emit anything, right? But that's pretty tricky to get right. And PyPy actually doesn't do that. So PyPy wouldn't even do this example. PyPy only does this if the right-hand side of these stores is itself a freshly allocated object, and the store would escape that. Right?
If the right-hand side?
So if we don't have a 5, if we don't put a 5 in there, but instead we put the result of an alloc, then we have extra incentives to not actually do that store. Right? So only in that case does...
This is what we did the other day then.
It relates to it, yes.
Yeah.
Right. So yeah, let's wrap up slowly. I mean, we can. Are there things that people want to ask us, or Max? Can you push this like to a
yes
somewhere?
1 second, please.
Mm-hmm. Maybe you can exfade the test so that we know that it's not supposed to pass.
How do you do that?
There's a decorator called pytest.mark.xfade. No, just .xfade.
Ah.
Mm-hmm.
Oh, I already got PyTest.
Yeah.
All right. All right, then I'll add a remote. All right. I'll leave you open for questions while I do some nonsense.
What do you mean with good lazy evaluation? You mean with good store syncing? Yeah, I don't quite know how good like real proper JITs are at sort of delaying stores. I would kind of suggest that something like Hotspot or so is pretty good at reasoning about the heap. But yeah, I honestly don't quite know. Yeah, it would be interesting to try and see how good the JavaScript JITs do this. I honestly never looked. I mean, but it gets hairy. I mean, it gets hairy pretty fast. Face, yeah, sure. I mean, you're welcome. That was kind of the motivation for this a little bit too. That there's quite a bit of sort of nice write-ups for front ends and back ends, but sort of the thing in the middle where you try to make the code better is a lot harder to approach. And so, yeah, and I think production compilers tend to not be very readable. I mean, so the whole reason why I started writing these tiny optimizers is that somebody like Thorsten, who is or was also on the stream, asked me whether I can point him to some PyPy code that does that kind of stuff. And basically, I looked at it, and it's definitely not very readable, and you need to sort of find your way around sort of hairy and complicated code.
I mean,
so
I think it can be readable, though. I think, right, you pointed me to some stuff, and I mean, maybe the float math is easier, but and you can look at the float optimization and be like, oh yeah, that makes sense.
Yeah, I mean, basically, I think
guide.
You can scaffold up, right? I mean, if you understand this kind of stuff that we've been writing here, you understand some of the sort of architecture and some of the mechanism of what we're using in PyPy. And so yeah, with that as a background, it might become more readable. But I think if you just start there, it's a little bit confusing. Max, can you maybe paste the URL into the chat so we don't have to like type all the hex?
I don't have access to the chat. I don't know how to do that.
You don't have access to the chat. Yeah, then can you send it to me in private chat?
I sent it to you in Twitter, but I can do that too.
Oh yeah, that's fine too. Okay, I paste it into the chat. So QueryFace, about basic blocks, yeah, that's an excellent question. So you would, I mean, there are various ways to scale that up. I mean, so real, like if you're talking about C compilers, it's actually quite hard to scale it up what they're doing, because they do a lot more analysis. I mean, one of the fun properties of the optimizer that we've been writing today is that it's basically one pass. It goes over. There's no separate analysis phase, right? We don't have a phase where we learn heap properties and then a second phase where we use it to optimize the block. Instead, we just learn things and then immediately use that knowledge, right? And so if you want to scale it up to like general control flow graphs, you definitely have to sort of be much more careful about separating the analysis phase from the optimization phase. Max, can you still hear me?
Yes.
Okay, I tried to write something into the chat and it says I don't have internet, which is kind of interesting. But if my voice is still getting through to gate, okay, I'm going to ignore that comment. Right, so if you want to scale it up to like general control flow graphs, things become fairly tricky. And then indeed you need to think about lattices. And then you usually separate out the analysis phase from the optimization phase. There's actually like an intermediate step. You can scale up what we've been doing to sort of subsets of control flow graphs. You can do it like if you leave out loops, things become much simpler. And if you leave out so control flow merges, things will also become a little bit simpler. So you can apply these techniques that we've been using in the stream today. You can apply them. You can scale them up to having some amount of control flow, but basically not all of it. But that I mean, there are a lot of situations where sort of limited control flow is still great if you can optimize just that. And in fact, like a lot of the R Python optimizers will actually just deal with these limited cases of control flow.
So the insight there is that if your control flow is functionally a trace in that it doesn't have backwards edges or merges, then you can do it.
Actually, what I learned today, not really today, what I learned this week when reading some of the original papers that contain some of the ideas that we've been discussing, I learned that you can even deal with merges a little bit. The really complicated case is loops.
Right? Your message
loops, yeah, my message made it, right?
Loops, do you have to like fix point or something, or do you just say you just kind of give up?
So for loops, so in PyPy we have an extra mechanism for loops, and it's basically the same mechanism that LuaJIT has been exploring. You can do really well with loops by peeling off one iteration and then applying these techniques that we've been discussing.
So but a basic block that's a copy of the loop body at the top.
Yes, but then for really complicated control flows with nested loops and so on, you really need to do proper work and proper abstract interpretation and proper like fixed point analysis, where you keep changing your information until it doesn't change anymore, and then you know that the information is correct for all the possible variations of all the possible control flows.
So Chicken Bruda, regarding inlining, I mean, I think we could totally do a stream. I can walk. So the PyPy function inliner is probably just the trace, right? Do you have any actual inlining?
No, our inliner is really weird, and it's not that great. So
right. So we could do a stream of our team's compiler's inliner, which I am familiar with because I wrote it. If that's interesting to anybody, it's for Python.
Yeah, that might be fun.
But it's written in C++. There's a lot of extra stuff
that might be less fun. Let's not do that then.
It's readable. It's readable though.
Cool. So yeah, any other questions or wishes for things that I should opine upon? Otherwise, I think I would wrap up now. Yeah, let's wait for another minute.
You could send a link to, if you're so inclined, to my PL resources page, which has compilers that I think are readable. I don't know if that's port the inliner Python. Oh man. Yeah, it has some infrastructure that I mean, it's not impossible.
Actually, I think PyTorch has a pure Python inliner, if I remember correctly. But I'm not really familiar with its architecture.
I did want to build RJIT in Python because it's much nicer. You don't have to deal with anything, and just like dead code elimination is the garbage collector. But the problem is, if you need to compile quickly, you're a little bit hosed, and if you want to compile in parallel, you're super hosed. So we don't do that.
Right. Yeah. I mean, it's not super easy to do that. But yeah. I mean, I don't really know how PyTorch works. I should talk to some of the PyTorch people again. They only support a subset of Python, but I think their inliner is written in Python. I think they're less performance sensitive to compile time. Yeah. Okay, I would say that's it. Thanks, everybody. I had loads of fun. That was great. I'll try to also upload this to YouTube. Max, is that okay for you?
Sounds great.
Okay, wonderful. Yeah. Thanks a lot, Max, for doing all the typing and talking to me.
And thanks for walking me through it. I can only do one or the other. I can't do both at once. So thanks for doing the other part.
Wonderful. So thanks, and let's do this again sometime. Goodbye.
Ciao.